This is AMT Live Studio. I am your host. I teach AMP as a registered nurse and anatomy and physiology instructor for advanced level healthcare pros. So today, we're going to tackle one of the most fundamental questions in all of biology. Why do we age? And we're going to look past the idea of aging as just a number on a calendar and instead understand it as a core biological process, one that we might even be able to modify.
So here is our roadmap. We'll start our journey with a patient's story, just to ground all of this science in a real-world context. Then we'll set a baseline by looking at what youth actually looks like physiologically. After that, we'll dive into the core cellular hallmarks that really drive the aging process. Then we'll connect those tiny cellular changes to the symptoms we see in our patients, talk about the fascinating new science of measuring biological age, and finally, we'll look to the future, at how we might extend not just our lifespan, but more importantly, our health span.
All right, let's start where it always matters the most, with the patient. We're going to use a clinical observation to really anchor the complex science that we're about to get into. So let's meet Elena. She's 82 years old, and while she's still living independently, she's finding that just getting through the day is getting tougher. Her experience is incredibly common, and it gives us a perfect window into the physiological processes of aging. Now, if we were to talk with Elena, she'd describe a handful of issues that are probably very familiar to anyone in geriatric care. She feels this deep, unusual tiredness, a classic sign of frailty. She mentions that even walking across a room is becoming a challenge, which immediately makes us think about her risk for sarcopenia, that's age-related muscle loss. Her balance feels off, and that's making her genuinely afraid of falling. And like so many older adults, she's managing a whole list of chronic conditions: hypertension, arthritis, high cholesterol, with multiple different medications, a situation we call polypharmacy. And all of this brings us to the central question of geroscience. Is it just bad luck that conditions like heart disease and arthritis and frailty all seem to show up around the same time? Or could there be a single, underlying process that's actually driving all of them?
To answer that, we first have to understand our baseline. Before we can really dig into what goes wrong in the aging body, we have to quickly review the normal, healthy physiology of a youthful one.
Think about it. When we're young, our bodies are like these amazing, well-oiled machines that come with a fantastic maintenance crew. Our cellular repair systems are strong and super efficient, and if a cell gets damaged so badly it can't be fixed, it gets taken out of the system and replaced by a brand new, healthy one. This constant upkeep keeps all our tissues and organs working at their peak, which allows the whole system to bounce back from stressors, like an infection or an injury, with incredible resilience. Okay, so that's the ideal. Now let's zoom in, way in. We're going from the system level down to the cellular and molecular level, because this is where the aging process really begins, driven by a set of predictable changes that we now call the hallmarks of aging. Now, one of the most important hallmarks to understand is something called cellular senescence. And it's a fascinating state. See, when a cell gets significantly damaged, say to its DNA, it can enter senescence. It permanently stops dividing. Now, that's actually a good thing because it stops it from becoming cancerous. But here's the crucial part. It doesn't die. It just hangs around. Really, the best way to think about these cells is as zombie cells. They've stopped doing their normal jobs, so they're not contributing anymore. But they're not just taking up space. Instead, they stay metabolically active and start spewing out a whole cocktail of harmful substances that damage the healthy tissue around them. They are, quite literally, the living dead of the cellular world. And as this diagram shows so well, cellular senescence is just one piece of a much larger puzzle. There are actually 12 proposed hallmarks that all seem to work together to drive aging. Let's just touch on a couple more. See telomere attrition right here? Telomeres are these little protective caps on the ends of our chromosomes, kind of like the plastic tips on a shoelace. Every single time a cell divides, those telomeres get a tiny bit shorter. Eventually, they get so short that the cell can't divide safely anymore, and that's a trigger for senescence. And then over here you see mitochondrial dysfunction. Our mitochondria are the powerhouses of our cells. As we get older, they just get less efficient. They produce less energy and more damaging byproducts. The main thing to remember is that these aren't separate issues. They all influence each other, creating this domino effect that speeds up aging across our entire body. So how exactly do these zombie cells cause so much trouble? Well, they secrete something we call the senescence-associated secretory phenotype, or SASP for short. This is that toxic cocktail I was talking about. It's just loaded with pro-inflammatory signals, things like cytokines and chemokines that are basically alarm bells for the immune system, plus enzymes that literally break down the healthy tissue next door. This whole process creates a state of chronic, low-grade inflammation all through the body, a condition so central to aging that scientists have even given it a nickname, inflammaging.
Okay, so we've seen what's happening on the microscopic level. Now let's zoom back out to the big picture and connect these cellular changes to the real-world signs and symptoms that we saw in our patient, Alina.
And this illustrates that connection perfectly. The molecular hallmarks don't just stay at the micro level, they directly cause observable physiological problems. That sarcopenia and frailty Alina's feeling, that's linked to senescent zombie cells building up in her muscles. Any cognitive decline we might see is tied to neuroinflammation driven by that SASP cocktail. Poor cardio fitness? Well, that can result from mitochondrial dysfunction and senescence in our blood vessels. The link from the cell to the symptom is direct.
And we're not talking about a minor problem here. The data is pretty staggering. A full 53%. That's more than half of Medicare beneficiaries between 65 and 74 are living with multiple chronic conditions. And that is not a coincidence. It's a direct result of this underlying aging process hitting all of our body systems at the same time.
So this is the crucial point, the big takeaway. The geroscience paradigm completely reframes how we look at disease. It suggests that aging itself is the single biggest risk factor for almost all major chronic diseases. Cellular senescence and chronic inflammation don't just cause old age. They are actively driving heart disease, cancer, type 2 diabetes, and Alzheimer's. They are the common root of the problem.
Now, if aging is a biological process and not just time passing, that implies that we should have better ways to measure it. And this shifts our focus from how many years someone has been alive to how aged their body actually is on a functional level.
And this slide really nails the key difference. Chronological age, that's just the number of years since you were born. It's a constant. Your biological age, on the other hand, reflects the true functional state of your cells and your organ systems. We can even estimate it now using things like epigenetic clocks. So you can have two people who are both 70 years old chronologically, but have completely different biological ages. And here's the most exciting part. While you can't change your chronological age, all the evidence suggests that your biological age is potentially modifiable. And this idea, the fact that we might be able to actually modify the aging process, brings us to what is truly the new frontier of medicine, the goal of extending our health span.
Let's be really clear about these two terms. Lifespan is just the total number of years you live. Health span is the number of those years you live in good health, free from the burden of chronic disease and disability. For decades, the goal of medicine was just to increase lifespan. The new goal is to make sure our health span matches our lifespan. It's about quality of life, not just quantity.
So how might we do this? Well, researchers are developing some really exciting new strategies that target those hallmarks of aging directly. See how these line up with the problems we just discussed? Senolytics are drugs designed to hunt down and destroy those zombie senescent cells. Senomorphics are a little different. They don't kill the cells, but they shut down their ability to secrete that harmful SASP. And of course, we can never forget lifestyle. Interventions like exercise and calorie restriction have been scientifically shown to impact these exact same pathways. But ultimately, extending health span is going to require a holistic approach. It's not just about finding a magic pill, it's about how our behaviors, the clinical care we get, our social and economic situation, and even our physical environment all work together to determine how well we age. And this leaves us with a really powerful thought to end on. The geroscience paradigm asks us to imagine a future where we stop playing whack-a-mole with individual diseases. What if, by targeting the biological process of aging itself, we could delay or prevent not just one, but many of the chronic diseases of aging all at once? That's the revolutionary promise of this field. This has been A&P Live Studio. Thank you so much for joining me. And please remember, this presentation is for educational purposes only. It is not intended as medical advice, diagnosis, or as a substitute for professional healthcare decisions.